Hey everyone, and welcome to this explainer. Today, we're taking a really fascinating journey from basic abstract theory all the way down to advanced algorithmic optimization in Java. We are going to completely master stacks, and I promise you, by the time we wrap up, you're going to look at everyday software in a totally new light.
Have you ever just stopped and wondered how your browser's back button actually works? Or how the undo feature in your favorite code editor seems to perfectly remember your last mistake? Or, even how the Java virtual machine manages its own function calls right under the hood? Well, they're all secretly powered by this brilliantly simple data structure known as a stack.
So, here's our roadmap for today. We'll start with ADTs and LIFO principles, then cover core Java stack operations, followed by arrays, interfaces, and exceptions. After that, we'll solve the stock span problem, and finally dive into amortized analysis for growable stacks.
Let's jump straight into Section 1, ADTs and LIFO principles.
Before we even think about typing a single line of code, we really need to nail down what an abstract data type, or ADT, actually is in computer science. Think of it kind of like a TV remote. The remote gives you buttons for volume and power, right? That's the what. It's a formal contract specifying the rules of interaction. You don't need to know anything about the internal circuitry, the complex wiring, or the infrared signals. That's the how. An ADT completely separates that public specification from the messy internal implementation.
Now, for a stack, the absolute golden rule of its ADT is LIFO. That stands for last in, first out. It's exactly what it sounds like, a principle where the last elements you insert into a dynamic set is the very first one to be removed. It's just like a stack of plates at a buffet. You're only ever going to add a new plate to the very top, and when you need a plate, you grab it right off the top. You'd never try to rip one out from the middle. Entry and exit happen from the exact same end.
Moving on to Section 2, core Java stack operations.
Okay, so we've got the LIFO rule down conceptually. Let's look at the actual toolkit we use to interact with it. To make this super easy to remember, we'll use the PPTSI mnemonic. These are the 5 fundamental axioms of a stack. You've got push, which inserts a new element at the very top. Pop removes and returns that top element. Top, which is sometimes called peek, lets you look at the top element without actually removing it. And then we have 2 support methods, size to count the total elements, and isEmpty to quickly check if the stack has 0 elements. That's it. That's our entire toolset.
Which brings us to Section 3, arrays, interfaces, and exceptions.
What's really cool here is how Java actually enforces that TV remote contract we talked about using an interface. The interface dictates the what, but as engineers, we got to handle the dangerous edge cases. Think about those pop and top methods for a second. What happens if you try to pop a plate off a completely empty buffet stack? Well, in Java, we can't just let the program silently fail or crash unexpectedly. We handle this by explicitly throwing a stack empty exception. It delegates the error handling gracefully to the programmer, keeping the whole system robust. But here is the absolute kicker, performance. When we build our stack, we're using a fixed-size array under the hood, let's call it an array stack. We just keep track of an index pointer for the top element. Because arrays in Java let you instantly access memory via that index, every single core operation, pushing, popping, checking the top, runs in lightning-fast, constant time, O of 1. Whether your stack has 10 items or 10 million, it requires almost 0 computational effort. It is instantly fast.
All right, Section 4, solving the stock span problem.
Let's pull this out of the classroom and drop it right into a high-stakes, real-world technical interview scenario. This is exactly why stacks are so crucial. The challenge is the stock span problem. You need to find the maximum number of consecutive previous days where a stock's price was less than or equal to today's price. In financial analysis, understanding this span helps traders identify momentum. It sounds pretty straightforward, but how you actually write the code for this makes all the difference in the world.
Let's trace this out with some mock data. On day 1, the price is $60, so the span is just 1. It's just itself. Day 2 rises to $70, meaning it's higher than day 1, so our span accumulates to 2. Now day 3 drops back down to $60. Because the previous day was higher, the span resets completely back to 1. But look at day 4, jumping all the way to $75. It's higher than days 3, 2, and 1, giving us a span of 4. See the pattern? The span accumulates when prices rise, but resets the second they fall.
Now, if you panic and go with a naive approach, you'd probably use nested loops, looking backward day by day. But here's the trap. Every time the dataset grows, the processing time multiplies, resulting in an agonizingly slow quadratic time complexity, O of n squared. But By bringing in a stack to push and pop the indices of previous days, we can slash that processing time down to an elegant, linear time complexity, O of n. This right here is the true power of choosing the correct data structure.
So how does this stack actually do this? Well, for every single new day, you follow 4 simple steps. Step 1, check the top of the stack. Step 2, if the price at that top index is smaller, pop it off, because we literally just don't need it anymore. Step 3, calculate your span by simply subtracting the new top index from your current index. And Step 4, push your current index right onto the stack. By the way, here's a massive tip for your next technical interview. Anytime you hear a phrase like nearest greater or previous greater, your brain should immediately yell stack.
Finally, Section 5, Amortized Analysis for Growable Stacks.
Okay, we've got to talk about the elephant in the room with our array stack. What happens when our fixed-sized array gets completely full? Standard Java arrays have a rigid, fixed capacity. If we set our array up to hold 1024 elements, what on earth happens when we try to push element 1025? We can't just throw a stack full exception and call it a day. We need a dynamically resizing, growable stack.
We're basically looking at 2 options here. We could use a tight strategy, where we just add a small, constant number of slots, like say 10 new slots every time we hit the limit. But that forces us to constantly create brand new arrays and copy all our old data over and over again, which is incredibly expensive memory-wise. The vastly superior alternative is the growth strategy. Instead of adding a few measly slots, we completely double the size of the array's memory.
This doubling strategy is literally a game changer. By jumping from 10 slots to 20, then 40, then 80, we guarantee that the super expensive data copying operation happens less and less frequently as the array grows larger. Sure, that one specific push where the resizing happens takes a bit of time, but the vast majority of your future pushes, they're just effortlessly dropping data into empty, pre-allocated slots.
And that brings us to this absolutely beautiful mathematical concept called amortized analysis. It's simply the average cost of an operation over a long sequence of operations. Amortized analysis proves mathematically that because that expensive resizing happens so rarely with the doubling strategy, the average cost of every single push operation remains an incredibly efficient O of 1. The heavy lifting is completely averaged out over time. It's just brilliant.
There's a great quote from our source material that hits the nail on the head. Understanding these optimizations separates good code from great software engineering. Knowing how to write a simple loop is one thing, but deeply understanding how memory allocation works under the hood of Java collections, that elevates your entire approach to problem solving.
So I want to leave you with one final, kind of provocative thought. How might relying on the hidden array resizing of stacks actually be impacting the performance of your own favorite apps right now? These deeply embedded, amortized data structures are silently dictating the speed and efficiency of modern software all around us. Definitely think about that the next time you effortlessly hit that undo button. Thank you so much for joining me in this explainer, and keep exploring.